let's take the system of three equations with three unknowns. It's a quadratic system, and as it will soon turn out, the system has no solution. So what we could do is we could find the determinant of the matrix of coefficients, and that determinant would be 0, which would only mean that the system doesn't have a unique solution, but we couldn't judge from that determinant being 0 whether we have no solution or infinitely many solutions. Gauss-Jordan method will provide us with a straightforward answer. So we start with creating the augmented matrix, which is a matrix of coefficients with x, y's, and z's, and the matrix of the free coefficients, the right-hand side of the system. Okay, we're going to use Gauss-Jordan method with pivoting so as to avoid unnecessary interchange of rows. We choose any element to be our pivot. Obviously the first column is already a pivot column. You have 1 and zeros only, so one of these four entries, whichever, I'm going to choose this one. There's only one non-zero entry in this column, so only one operation to make this a 0, which is from that 3 we have to subtract 3 times 3 in row 1. The first row won't change. The second row will change, the third row won't. So here we have 0, 0, 0, and 0 plus 6, which is a 6, and the third row unchanged. And now if you look at the second row, what we have here, and when we change it into an equation, you have 0 times x plus 0 times y plus 0 times z equals 6. Which is of course not true. It's a contradiction. And what that means is that this system has simply no solution. If such a situation occurs at any point in your Gauss-Jordan elimination, that you have on the left-hand side you have a row of zeros and a non-zero entry on the right, it always corresponds to an equation which makes no sense. So in such a case you will always have no solution.